Welcome to this quick start guide on developing high-resolution weather models with NVIDIA Earth-2. Earth-2 is a family of open models, libraries, and frameworks for GPU-accelerated weather and climate simulations. We will walk through the process of training a state-of-the-art diffusion model using the tools available in NVIDIA PhysicsNeMo, an open-source Python library for physics AI. These tools will save you headaches when experimenting with different architectures, hyperparameters, and datasets. Diffusion models are what made modern AI image generators suddenly much more useful for everyday use cases. Diffusion models are a core building block of generative AI because they are trained to learn a data distribution and can then be used to generate new samples from it. Diffusion models are also ideal for tasks like downscaling and high-resolution forecasting because they are able to produce the fine-scale details required for weather modeling. They do not suffer from blurring like non-generative methods such as regression models, and they can model chaotic systems in a probabilistic manner. With downscaling, for example, we can turn a coarse resolution forecast or a reanalysis into a high-resolution version that captures local patterns. High-resolution forecasting allows us to evolve a model-based analysis or gridded observations, such as satellite or radar data, forward in time. Because AI models are fast and easy to run, they are ideal for rapidly updating nowcasting systems, producing ensemble forecasts, or for being applied to large data corpora. The theory of diffusion models is based on a so-called forward process that gradually adds noise to a data sample and a reverse process that removes this noise. A diffusion model is trained to recognize the noise added to a sample. It can then be used to transform pure noise into a realistic sample through a multi-step process. During training and inference, we supply the model with additional non-noisy data. This allows the model to be conditioned on inputs like coarse resolution weather for downscaling or the previous time step for forecasting. Additionally, we can use data like the regional orography. PhysicsNeMo also allows us to add categorical data, for example to make a forecasting model aware of the current lead time. PhysicsNeMo is NVIDIA's open source Python library for physics AI. Its applications span domains such as healthcare, energy, and manufacturing, as well as weather and climate. PhysicsNeMo is a modular toolkit that provides building blocks and end-to-end examples for training deep learning models. One of its strengths is that it makes scaling to multiple GPUs straightforward. We will take a closer look at the PhysicsNeMo Stormcast example, which combines the research from 3 weather models: Cordiv, Stormcast, and StormScope, with additional insights gained from applying diffusion models in practice. For demo purposes, we will train a downscaling model using ERA5 as a low-resolution data source and DANRA as the high-resolution data source. ERA5 is the 5th version of the ECMWF reanalysis provided by the Copernicus Climate Data Store. It is available at a 1/4 degree and 1 hour resolution. DANRA is the Danish Regional Atmospheric Reanalysis provided by the Danish Meteorological Institute. It is available at a 2.5 km and 3 hour resolution. Our model will be trained to emulate DANRA based on ERA5 and thus to increase the input resolution by approximately a factor of 10. The only component requiring a custom implementation before training is the data loader, which is specific to your training data. Everything else is handled by PhysicsNeMo. The data loader is a PyTorch dataset and hence implements the getItem method, which returns a single sample, in our case, the data for one timestamp. We return a dict with 2 keys. State contains the high-resolution DANRA data, and background contains the low-resolution ERA5 data. When training a forecasting model, background is optional, and state is a 2-element tuple containing the high-resolution data of the current time step and the next time step. The training configuration is managed with Hydra, which means that it can be split across a hierarchical set of files. The main components describe our data loader, the model architecture, the training hyperparameters, and the diffusion sampler. We will use a UNet with 5 layers, but you can also use a diffusion transformer. With diffusion transformers, PhysicsNeMo supports splitting the geographical domain across multiple GPUs, enabling large-scale use cases. You are free to define the dataset configuration based on your data loader implementation. In our case, we pass the input and output variables, and the paths to the training data and the files with the orography, land sea mask, and normalization constants. The entry point for training is train.py. You simply pass the name of your Hydra configuration and a name for your experiment. You can override parameters using regular Hydra syntax. The training routine can log to TensorBoard and weights and biases. You will be able to monitor the training and validation losses, output spectra, and samples generated from your validation set. Typical training runs require on the order of hundreds of GPU hours, which means less than 3 days of work clock time when training on multiple GPUs in parallel. Continental scale use cases will take on the order of thousands of GPU hours. After training, you can export your model and use it with NVIDIA Earth-2 Studio, an open source Python library for AI weather inference. Earth-2 Studio provides a slew of pre-trained models, data sources, I/O handlers, and tools for building inference pipelines. We can now, for example, emulate DANRA at 1 hour intervals instead of the 3 hour intervals we started with by applying our model to the 1 hourly ERA5 timestamps. Or we can create an ensemble. Even large ensemble sizes are feasible because inference time is typically in the range of seconds per ensemble member. With Earth-2 Studio, it is a one-line change to switch the input data source, so we can, for example, also test our model on GFS or IFS. If you're interested in more details, check the README in the PhysicsNeMo Stormcast example. We will also put a link to an extended workshop recording and accompanying code in the description. Thanks for watching.